this is a robust sign that we're returning back to normal. So yeah, let me start. And because we also have people joining in remotely, feel free to let me know if you can't see anything I write, or if my audio is off or something. Just shout or tell someone else and we'll figure it out. Okay, so let's start. So over the last 2 years, I've been working on a precise and rather general correspondence between lattice and continuum quantum field theories. The precise question is as follows. So given lattice theory, given a quantum theory which is non-perturbatively well-defined, completely finite with a dimensional Hilbert and an explicit Hamiltonian, how do you extract from that theory continuum theory with all the continuum structure that we are used to? And I don't mean just some few point correlators or some leading term in a free energy. I mean, how do we extract things like type 3 von Neumann algebras, or operator product expansions, or interesting universal counter terms and things like that? So how do we go beyond simple correlation functions and extract the actual interesting continuum meat out of some large but ultimately finite and very explicit lattice theory? So that's the general question that motivates me. Now, since I have 1 hour and not 1 week, I will not be able to talk about this in general, but you may have noticed that I have a series of papers on this subject from earlier this summer. But today I'm going to focus on one specific example that is very simple in some ways and very, very complicated and interesting in other ways, and that's Chern-Simons theory. So there is perhaps no other simple example of a theory for which we have a very simple continuum understanding where we can do many things, and yet for which we do not possess perfectly finite lattice description with no shortcuts taken or something like that, with a completely explicit between lattice and the continuum. I want to discuss this problem a bit, and I want to propose sort of 2 ways to approach this correspondence. Basically, it will turn out, at least at this stage of my understanding, I will claim that there essentially are 2 different notions of continuum Chern-Simons theory that one should talk about. That one that you may call the induced Chern-Simons theory, that you associate to things like effective theories of massive fermions and so on. And on the other hand, you have something you may call, proper Chern-Simons theory that you associate to some actual lattice gauge theory. And these 2 things, which in the continuum see the same action, really come from different microscopic origins. And to date, I do not know of an actual connection between the 2. So I'm going to describe how each of them separately come about. The entire top content of the talk today is actually something that has not been published in as much detail. So details and some calculations are in this paper, which is 3 of my epic trilogy. But a lot of the details have not been published and have not been worked out, so it's a work in progress. So hopefully nothing will be wrong, but it's very likely that some of the statements I make will be streamlined and simplified in the future. So with that said, let me start. So as I said, the talk 2 parts, because I will talk about 2 manifestations of Chern-Simons theory. So part one will be what you may call induced Chern-Simons theory. The philosophy here will be as follows. We know how to lattice and how to properly think about fermionic theories, massive or massless. And we also know from the 80s onwards that generally integrating out massive fermions, or whether with an explicit mass or a gap that's induced by a magnetic field, ends up giving us effective Chern-Simons term in the effective action. So knowing this, one way to attack and try to formulate Chern-Simons starting from some kind of finite lattice theory is to study what happens with massive fermions on a lattice and see in what sense you get some kind of Chern-Simons theory arising from that. And again, I will not assume there will not be any infinities in anything I say. So there are a lot of calculations that are similar to each other, but they all, as far as I know in the literature, assume that something is infinite, either that the lattice is infinite, or that there is, or that there is. Where there will be even less room for subtlety, where everything will be extremely explicit and where you don't have any excuse not to get everything right. Except for minus signs. I might get minus signs wrong. I think it'll be mostly correct. And the second part of the talk will be concerned with specifically Hamiltonian lattice gauge theories. With flux attachment. So this is a rather novel class of Hamiltonians for gauge theories, which were introduced in order to generalize the Djordje-Radicevic transformation in some earlier work I did with Johan and Anton Kapustin. It turns out that it's really regime of some of these theories, not the topological limit, but the confined limit of some of these lattice gauge theories that gives you Chern-Simons actions. It doesn't give you completely arbitrary Chern-Simons actions. There are some subtleties. There is an analog of a doubling problem, and I'll make that precise, but it's a very intuitively clear way to attack what we mean by Chern-Simons theories. You can think of this as a sort of Hamiltonian and much more microscopic and an even more explicit version of the the previous work that was done on this subject by I guess Eliezer and Semenoff and John Fratkin collaborators. I think some of them are in the audience. So this is a Hamiltonian version of this of a similar story. So now okay, that's the thing. Okay, so far I haven't really said anything technical. So if you still nevertheless have questions, feel free to let me know. If not, I will start with the actual details. Okay. Is there a working clock in the room? Is there a clock that works? No. Okay, I'll use my phone. Okay. Yes, that's okay. Okay, I'll use. Okay. Yeah. Thanks. Okay. So let me start with by talking about induced Chern-Simons terms in 0+1. It's a very simple story. It's very cute, and it generalizes fairly straightforwardly to higher dimensions. So consider a massive fermion in 0+1 dimensions. So it's really a system with a two-dimensional Hilbert space. So fermion or qubit, it doesn't really matter how you call it. And a Hamiltonian will be just this with m some real parameter and psi just the standard raising operator, or lowering it, I guess. Okay, so and this is nothing more, of course, than just than this matrix. So of course it's trivial to diagonalize. I mean, it's already diagonal, and everything can be solved exactly. And the only interesting fermion bilinear is, of course, just this one. And the only interesting current correlation function that you need to calculate at some temperature beta is just going to be given by this. And in particular, at low temperatures, this is going to be given by 1/2 1 minus sine of m. Okay, so this is the explicit microscopic value of this correlate. Everything is completely exact. So what can we do here? In what sense can we start talking about massive fermions giving rise to some effective Chern-Simons function or anything like that? Well,
sorry, I have a comment.
Oh, sorry, Eduardo?
Yeah, I have a comment. Here,
Yes.
M, in this case, really is not a mass, but it's a time component of a gauge field because it couples linearly to the density. And so this is a gauge theory in reality.
You're saying this is a gauge theory?
Yes.
I mean, you can, yeah. Okay.
So you shouldn't call it a mass or chemical. It's like the chemical potential if you want, but.
Sure, I'm sure, but we can certainly agree it's just a nomenclature. It's just a question of notation at this point. Right?
I mean, yeah. So there is a story of this involving the parity anomaly, but the real issue here is this is not like the problem of the mass.
Oh, sorry, someone muted you. I could not hear.
Hello?
Yeah.
Yeah, so it's different in 2+1 dimensions. Okay, there is a distinction.
Yeah. In 2+1, it will be slightly different, of course. Then I will have to worry about different. Then I'll have multiple currents, and I'll have to worry which one I'm turning the mass on for. But yeah. But in 0+1, this is there's no ambiguity. There's nothing to worry about. Yeah. Yeah. So yeah, if you want, I can call it mu, but it will not change any of the physics, of course. But yeah. And in particular, there's nothing no spatial. There's nowhere to put any gauge fields specifically or anything like that. So at a canonical level, that's all there is going to be. Interesting things will start happening only when I start trying to calculate this using path integrals. So how do I calculate this kind of thing using integrals? This kind of correlation function? Well, there's of course a well-known story. And correlation function integral by the standard Brandais. I can write it as some integral of some Grassmann variables. And I will write it very carefully. So here, I will have the time, which will belong to this interval, where d tau is just beta over n0. where n0 is very large. And these etas will be my Grassmann variables, and x will be an action which will look like this. Okay, so and in particular, I'm being very right at in the limit of m than 1. So that's why approximation here. So so as long as and I'm always free to choose n0 to be for this to be true for any mass. Okay, so good. So this is the action, and this is the standard thing you will see in all textbooks, of course. Now, the slightly non-standard thing I want to emphasize, and that I'm sort of already emphasizing by writing this in such an annoying way, is that at this level, there is no sense in which fields, these Grassmann fields, and eta plus d tau at time tau and d plus d tau are in no way close to each other. And in fact, you might say, okay, so maybe I can just Fourier transform this and get rid of the high frequencies or something like that, or indeed approximate this guy just this by saying, oh, my field varies smoothly, and I don't need to care about the higher derivatives. And the fact is, you actually can't. And at this level of simplicity, or convince yourself by just doing numerics that you cannot do this. So if you want to calculate something like this, that will eventually boil down to doing a sum over things that look like this: I omega n d tau minus 1 plus m d tau, where omega n's are, of course, the Matsubara frequencies. And even though this d tau is small, this sum will actually sensitively depend on omega n's that are of the order of 1 over d tau, which is order n0. So if you just drop these, you will get the wrong answer. Here we know the exact right answer. So and you can convince yourself in many ways, numerically is probably the best, that you actually cannot just drop high frequencies from a sum like this. You actually, at this level, you actually need them. You actually need delicate phase cancellations that come from these high frequencies in order to get the right result. Good. So that's a cautionary statement. And that's kind of annoying, because this kind of sum is difficult to do, as opposed to a sum you would get if you were just allowed to exponential, which is sort of implicitly done in all textbooks. So what you can do is the following. You can now replace this path integral calculation by a different one in which the fields are smooth, temporally smooth. So this will give you a new calculation. This will give you a new path integral problem to do that is a priori not even related to the old one. And what's going to save you is going to be a miracle of universality, as I will describe in a second. So, so explicit, let me define the Fourier transform. So a lot of this is, of course, StatMech or condensed matter physics 101, but in some ways, the upshot will be something that I have never seen anywhere else. So I think it's still interesting to stress. So let me choose my frequencies to go like this. where of course omega n is 2 pi beta n plus 1/2. So okay, so let's say you have these kinds of you define these linear combinations of these guys, and now let me define a projection that I will call temporal smoothing. To a new set of fields where I have just removed the highest frequencies. Like so. So where I have some relation of this form. So I have introduced a new large parameter ns, but in a particular scaling such that ns over n0 is small. So so these fields, by definition, are going to obey relations of this form. Simply because changing tau by d tau will just change this exponent here, and since this omega is limited by ns, you will have to get the difference can only be of the order ns times d tau, which is the thing here. So this is a way of imposing of smoothness onto your path integral variables, and it's really this that makes things tractable in the path integral, because now when you have you will get a new path integral, and you will have a new variable. Let me call it J, capital J, which you can define like this. So now you have the same things here, except now you're only working with smooth variables like so. And here you only have you have the same action, but of course projected such that you only have eta d eta minus plus m eta eta. And these are smooth variables here. So it's function of t, function of tau, function of tau, etc. So and so here you can actually calculate this by in the same way here, except you're now allowed all of your omegas that will appear in this sum are guaranteed to, of course, be smaller than the scale set by ns, and you will be able to expand this, and you will just do the standard sum using complex analysis methods, or however you want, and you will be able to get an answer analytically. And now the amazing fact that I do not have a super deep understanding of is the following. These two are not the same. So that's kind of expected, because I kept harping on the need to keep high frequencies here. So this fact is not surprising. This is just a different kind of calculation. But there exists this relation, which you can just confirm analytically, for whenever m times beta is much less than ns. And then there might be things like ns over n or something like that. Okay. So this will be obvious to varying degrees to different people. I'm sure maybe someone has done this calculation and seen this before, but I have definitely not seen it promulgated widely. Anyways, so this is a remarkable statement. A priori, as I said, these frequencies were wild, and like there was no need for there to be any nice relation between these two path integrals. Nevertheless, there is, and this thing here is what in modern literature you would call a contact term. So basically, you should think of this as a term you need to add your smooth path integral in order to produce the microscopically correct answer. You can think of this projection as some version of RG, but I prefer not to use those words here, especially because when I do it in a canonical picture, spatial and smoothing is different. RG will have a completely separate meaning from spatial smoothing. But at this level, you can get away with thinking of it as essentially RG. In that sense, it's not surprising you need to add some term, or which is a special case of a counter term, I guess. And it just so happens that in this case, it's exactly this.
Sorry.
Yes.
Can I say something?
Of course.
I think this is because it's just you are rediscovering the limit to the edge, for example, in the quantum Hall effect, which is one-dimensional fermions, and bosonization, because you are computing the current, okay, or the density, which is part of the current. And this 1/2 is just the renormalization of the chemical potential that comes automatically because you need it for Navier-Stokes boundary condition. So I think this is, I mean, you rediscovered the basically bosonization of one-dimensional fermions.
Okay, that's
and the fact that you have a mass is helpful to disentangle the scales, but if you don't have the mass, then you have to fix this 1/2 by hand by establishing the boundary condition of the fermions, or say on a circle, and so it becomes a problem of boundary condition of the field. But because you have a mass, it comes naturally by itself. If you do the calculation without a mass, so directly in the massless theory, then this 1/2 is free parameter, sort of normalization, finite normalization that you may have, and then you fix by some physical condition. So conclusion, your calculation is fine. Okay.
I should say though, there is one thing I did not
please
specify.
go on. I don't want to.
I want this. So my reply to me is that's the reason I haven't thought it through. So I'm not going to immediately say yes, but I'm going to just say there is around, which comes from actually computing the partition function, not the function. So the separate term calculate that you need to add when you're calculating the partition function. So if I were to calculate this z, this guy here, using the smooth path integral, then I would also find that there is a difference of e to the minus beta m over 2 compared to the, I forget if it's plus or minus, there's some sign. So there is this, but this is a separate issue. Because this actually just changes my free energy by 1/2, but this actually changes the correlator by 1/2. So they're different counter terms. So there are two 1/2s floating around, and I don't know if the one you is this one or one. That can probably be understood.
Hello. Yeah, the one I mean is in the definition of this.
In this.
Yes.
Okay.
Yes.
Okay.
Because it enters the normal ordering. Okay.
Yes.
If then you normal order, then you have to take when you normal order, you remove an infinite amount, which is your n0, removing n0, and then you have a 1/2. You still have the freedom to adjust the The finite constant.
Okay.
The finite constant, which is this 1/2.
Okay, good. So then if
Yes.
then we can discuss that more. But yeah, I believe
I agree completely with your
the
calculation.
correspondence is probably right. Yeah.
I don't. I mean,
Yeah.
please keep going.
Okay.
My
Well,
one was not a criticism. Please,
no, okay,
please
good.
go on.
Yeah. So anyway, so now you can kind of see where I'm going with this. So basically, the statement now is going to be the following: if you want to compute this guy using the standard generating functional method in the smooth path integral. So if I want to calculate something like J as some differential of a generating functional like this. So this has some factor of I and maybe tau, which I don't really care to fix right now. So if I want to do something like this, so this is a standard action, and now I add something like this. So if I want to do this kind of calculation, maybe I can do it like this. Then, in order to, if I'm going to do everything in a smooth way, so if I'm going to be working with smooth fields here and here, then the other thing I need to do is I need to add this factor of 1/2 d tau just A, because that factor will make sure that I get, this is more properly, I should write it the capital J, because that's a smooth one. So I will get this factor of J once I differentiate plus 1/2. Okay, so this is my 1D Chern-Simons term with an improperly quantized level. Of course, now you can add multiple fermions, and each of them will contribute a separate factor 1/2 level. And this is the one way you can start from a completely finite system here. And basically, as long as you are in a canonical picture, there's no Chern-Simons anywhere. But if you insist on doing smooth path integrals, then you will be forced to add this. So that's one lesson. And this here generalizes to higher functions, except toward spatial smoothness, and that's a new can of worms, which I will not today. But the same idea will hold. Basically, there you will have a correlator of 2 J's, which has to have some interesting imaginary part with this anti-symmetric epsilon mu nu rho. And in order to reproduce that thing, you will need to add a proper 3-dimensional term with a fractional coupling with a 1/2 level for a single fermion. Okay, so that's one story on how you can see the Chern-Simons term arising. It's really smoothing that forces you to do it. It's not the lattice itself. So these kinds of Chern-Simons are just visible on the lattice. That's lesson number 1. Okay. I'm going to start erasing things. So if you have any questions, feel free to ask now.
I have a comment.
There is a question. Sorry.
Yeah. Okay. So there is an old literature on problems of this type. In the continuum, there was an old paper back in 1986, I believe, by Elitzer and collaborators. There they make the point, when they write down the path integral as you do, that the quantity you're calling M is actually the time component of a gauge field, which is what the chemical potential is, by the way. And then there is a regularization problem there as usual, and you have an alternative. Either you keep time reversal invariance, which is or CP, whatever you want to call it, or you keep gauge invariance. the regularization that you have used, which is a standard regularization, is the one that is gauge invariant. And that amounts to an operator ordering problem in the Hamiltonian, this distinction. And so this is the origin of these 1/2s, essentially, that you are discussing here. They computed basically the fermion determinant using Pauli Villars. There's a similar discussion in the lattice gauge theory community back in the late 80s, I think, by maybe Simon Catterall. I forgot the actual, he was a postdoc here in Urbana, that's why I know that. And he derived an expression on the lattice for what this should be. And again, he wanted to use, like any lattice person, he wanted to preserve gauge invariance. And that's the expression that essentially leads to your first result. But you could have used another regularization that violates gauge invariance, but keeps time reversal, essentially the changing the sign of the vector potential, or M, whatever you want to call it. And so it's important that here, really, the quantity is not a mass in the sense of the fermion, of a Dirac fermion. It's more like a gauge field. And it's the only thing you can add in 0+1 dimensions is a time component. If it is constant, that we call it a chemical potential, correct? So that was the origin of my first comment. You really have an operator ordering ambiguity when you insist in working in the continuum. And then it depends on what symmetries you want to preserve, which is related. So this is the analog of the parity anomaly in a sense, because you're in an odd dimension space-time.
So I guess I should start by apologizing because for audio reasons, I got around 50% of that. And I don't know if anyone in the audience.
Is more or less the same comment.
Okay.
It's the same comment. This 1/2 is a regularization condition.
Yes.
That you have to choose according to some symmetry principle or something. Okay. In your case, you got 1/2, but it's not the only possibility. Okay. And but this is not a criticism to your calculation. So I think your calculation is fine. So you are discovering something
right. I mean,
in a different language,
right.
and so please go on because we are already out of time, in my opinion.
Oh no, it's okay. I think we'll be fine. But yeah, like
I think
I have to apologize to
Eduardo
for, like,
will forgive me for this.
I am happy to discuss by email or like or one-on-one Zoom or something when we can actually do, audio error correction at our own leisure. So, but so I agree. Like this is not be a surprise in some level, but I think it's certainly the nicest and sort of clearest way of finding this 1/2 that I am aware of. Certainly, if you are a pro at normalization, you will have, by this 1/2, just like people have done in 3 dimensions already. So in that sense, it's not a surprise. But it's nice to if you're asking yourself, what's the connection to completely trivial and well-defined lattice models? This is, I think, the one way to answer that. Okay. So next, I will say something about this other story. About these lattice gauge theories with flux attachments. So these are all Abelian theories. You should think of the gauge group as being dk. And here I am going to be generically in +1 dimensions. So everything is going to be on a spatial manifold, but so time will be, everything is going to be on a single time slice. So this and my degrees of freedom will be zk variables, clock variables living on links. And on every link of the theory of the lattice, I will essentially have 2 operators that generate algebra. So I will have a shift operator XL and a clock operator ZL. and they will act in the usual way. So this will, and Z. So these are just generalizations of the Pauli matrices, Z and X. And this A takes values from 2 pi, well, it's some periodicity, and this 2 pi over K I can call dA. You may think of it small for most purposes, but it doesn't have to be. Okay. Of course, we know that a standard decay gauge theory gauge constraint of the form at each site, at each vertex V of the lattice, you can define this guy for all A's that touch the vertex V. I'm using this notation like a version of the boundary operator. So basically, for every vertex V, I have all possible links emanating from it, and I multiply these x's and with different powers here, depending on the orientations of this lattice, depending on the exact definition of this one. Okay, so and so these things are called Gauss operators, and I can impose this constraint, which is just the usual gauge constraint or Gauss law. And then I will get that the only gauge invariant operators are these x's and Wilson lines, or Wilson loops, sorry, defined on faces, which I can write like this. And of course, maybe some Wilson loops around non-contractible circles, if my spatial manifold allows it. So so that's the situation that we normally talk about in a gauge theory, in a standard gauge theory. Then we also talk about the standard Hamiltonian, which is a ZK minus XL dagger plus 1 over 2G squared, sum over faces, 2 minus W minus W. This is a magnetic term that becomes D squared. This is the electric term that becomes D over dA squared. When G goes to 0, this theory has a topological phase. When G goes to infinity, this theory is in a confined phase. And of course, there's a lot to be said about what happens in between, especially when you couple this to matter. That's a very which I will not get into today, but I just set the stage for what's going on. Okay, so this is all nice and this is all completely standard. Now, what I want to stress, there are alternatives to imposing this kind of constraint. Any alternatives? Okay, fractons are of course one alternative, where you, instead of this one constraint, you impose 3 constraints in 3 dimensions, and then you get a lot completely different physics. But I'm going to be sticking to 2 + 1 dimensions. I'm going to impose simpler constraint, define a new operator called G, curly G. And I'm going to define it by multiplying this original operator G, straight G, by, just let me call it like this, by a set of Wilson loops. So basically, what I'm going to be working with is, this is my operator G, like so. Links. This is my point V. And then in addition to that, I add some Wilson loops to the mix. So maybe I can add this one, and I can add another one here if I really wanted to, or I can add them at I can add multiple kinds of together to form this guy, and have different charges. So this one can have charge Q1, this one can have charge Q, so on. So I can do this, and then I can ask, okay, what is the theory in which this constraint is satisfied? This is a theory with flux attachment. So, this is magnetic flux through some point. Then you have to have electric charges at some points. Like this example, you will have a magnetic flux through this one plaquette will come with electric charges at these two sites. It's kind of badly drawn, but you can convince yourself by studying this form. This is what happens. So this is already a hallmark of Chern-Simons theory, of course, that you have a constraint like this, except here we're essentially starting from that. And the reason why this is interesting to be, because the Z2 version of these theories work with Chern and Kapustin was shown to be precisely dual, exactly all operators mapping to actually just a pure fermion system in 2+1 dimensions. So it's a version of Djordje transformation will dualize, and the fact that fermions anti-commute will essentially dualize to the fact that there is this kind of constraint posed. This is not obvious, I think, but it's very intuitive depending on your education and upbringing and so on. And somehow it has not been explicit, even though, of course, we knew that there was a relation between fermions and Chern-Simons flux attachment going back 30 years, if not more. And of course, there were different versions of Jordan Wigner, but this one is completely general and works for every theory. It works at the level of operator algebra, not and so it's nice. And so this is all very nice, but what I want to focus on today is the confined version of this theory, an analog of this kind of Hamiltonian at large coupling. So what do I mean and by a Hamiltonian, the analog of this Hamiltonian? Well, first you need to ask what are the gauge invariant operators in this new theory. Yes.
Can you say again that the free fermion in this paper of 2017 is exactly dual to this theory, which is gauge theory, is Yang-Mills plus.
It's a pure Maxwell theory, if you will, with flux attachment.
So it's a so-called topological massive gauge theory of Jakiv and company?
No, not even that. So this actually works for any Hamiltonian. So it doesn't have to be free fermions on one side, and it doesn't have to be a topological gauge theory on the other side. It works, as I said, it works for every single operator. And the mapping is essentially going to be at each W in this gauge theory will map to a fermion density, will map to something like you can think of it as a product of two Majoranas, and Majoranas will live on the side. So there will be an I here. So this will be one mapping. These are Majorana operators, and the gauge invariant versions of these shift operators, which I will denote by curly X, that live on links, will essentially be dualized to products of basically, if this is your lattice, so you have this operator XL living on it, and then these, and you have operators, Majorana operators on dual sides, on both sides of this guy. So this will dualize to something like this. So there will be this of first linear gauge invariant and massive. So a massive theory, a massive fermion theory will just dualize to the G goes to 0 limit of this guy, but the generally.
So your answer is yes, and in fact more general.
Yes.
Okay.
Yes. I don't even think of it in terms of just the topological limit. Yeah, it's just a general observation. Of course, topological around, which I haven't really mentioned, but they don't really matter for most of the argument here. Okay. So, but I have already emphasized that the important thing is that there exist gauge variant versions of these operators. So the individual operator XL, the electric operator, is not gauge invariant anymore. It does not commute with this general curly G's. But there is a new version of it, which I will call curly X, which essentially amounts to multiplying this guy with an open Wilson line. So basically what happens is, and on every plaquette which has some attached electric charge, this operator curly X will consist of this individual X here and an operator Z. Let's call it X, and such that this operator W transports the attached charge from this. So from the point where the charge is attached to this in this plaquette to the point where the charge is attached to this plaquette. So so basically these guys will transport both magnetic flux, which is what these X's do, and attach these W's do. Basically, there is going to be some complicated product of a single X, a bunch of Z's, that exact rule function A of B, the exact choice of this curly G up there. The simplest way to think about it is on a square lattice. So let's say that we are on a square lattice, and this is our product of X's, and our flux attachment just says that this is curly G. So you only have this one W, and north in the east corner, and then you check that the operators that commute with this curly are going to be link, and there will be an and here. So X is another version of X. So so you can check that how I try to fit onto this guy, there'll be consistencies. Good. So so instead of using the original X's, we use these curly ones, and we can write down a Hamiltonian where the only difference is the use of these curly X's. Now we have a Hamiltonian in which you have 2 minus XL minus curly X dagger. So you can study Hamiltonian like this. Now I want to study a limit where the coupling goes to infinity. So where in the Hamiltonian essentially tries to just become a constraint thing that constraints of the form XL equal to the identity. So up to an important, let's study. Barring an important caveat, let's study this for. So a very nice. This is a very nice kind of constraint, a very interesting one. Because what it does, it says that, so if you think of Z as measuring the electric field. And if you think of x as essentially the momentum, okay, so you can actually see what happens here. Imposing this ends up saying that you have to have an equation of the form A1 is equal to A2 dagger up to various signs and stuff like that. So and constraint that relates these two and says that they have to multiply identity is just an equation of this form. This is the second constraint that you get in Chern-Simons theory if you just start studying the Chern-Simons section. The first constraint is, of course, flux attachment. That's already included. And the confined limit will enforce all the other constraints that you expect in a Chern-Simons theory. Okay, so this is all very promising. And the only problem, and it's a huge problem, is that these x's do not all commute with each other. So you cannot impose them all simultaneously. Okay, so finish in a few minutes. So this is a problem, and to 0th order, I do not know how to solve it. So this is almost getting Chern-Simons, but not quite, because I can't impose all of them at the same time. But I can do something else. I can be smarter than just imposing this condition and ask whether there exist flux attachment rules, which will actually give me commuting of curly x. And the answer is that there exist such constraints. In fact, I can, on a square lattice, I can give you, I can derive, I will not write it here because it requires notation and stuff, but there is a general relation that needs to be satisfied. So I can classify, I can write down the most general constraint, which gives me all commuting operators curly x. And the simplest example is an operator that looks like this. So it has the original Gauss operator, and then it has a W in the northwest corner, and it has a W dagger in the southwest corner. So it has two diametrically opposite operators included, and this here will have the curly x operators that look like this. So this is going to be x, and so there will be a z and there will be a z. One of them will be a dagger, but let's try to tell you in real time which one will be daggered. And the other one will look like this. So all the curly x operators will be products of three macroscopic operators like this. And now you can see that you start combining them. It's always going to be two of them that will overlap. You will never be able to make only this z overlap with this x and fail to commute, because there will also be this other x that will overlap with this other z. And so we will end up arranging them in such a way that the phases will all cancel and all the x's will commute with each other. And that's very nice. So then you can actually impose this constraint. And basically what happens is that you have you don't have precisely a constraint, but you have something like A1 at some point x plus A1 at some slightly shifted point x is equal to A2 dagger, A2 dat. So if you then proceed to smooth things out, you can believe that this is essentially the same as the original constraint. We're only shifting them by a single lattice spacing or something. So this is promising. And so the next natural thing and the last thing you can do that I will show you is to actually just write down the action that you get if you just try to the low temperature dynamics of this theory in this phase, in the confined phase where all of these constraints are satisfied. This action is easy to derive, and it turns out the action is going to be of the form let's say x and tau. So x are all my special sites, and tau are all the fields. And there will be two Hamiltonians, sorry, two different Lagrangians. And the Lagrangians will, just to be completely explicit, look like this. So the one I call L plus will look like this. So these E0s, E1s, and E2s are just unit vectors in directions 1, 0, and 2. So nothing too surprising there. Okay, so you will essentially get two Chern-Simons sections with these tiny offsets, but you know, we can believe that once we do an analog of smoothing that I discussed before, they will not matter too much. So let's not worry immediately about them. But basically, we get these two Lagrangians, and what we get is essentially two actions. So we get one Chern-Simons section minus another Chern-Simons section. And this is very reminiscent of fermion doubling in some way. So basically, we are not able to get a single Chern-Simons section, two of them. This has to be related to, you know, the standard story of the Chern-Simons generically being a spin TQFT and requiring a block in order to find and so on. But this is all completely fresh, and I not want to make any ridiculous claims just yet. For now, I will just say that this is sort of the closest I can get to deriving Chern-Simons, starting from a completely finite lattice system like this on an arbitrary lattice. I mean, the example I gave you was on a square lattice, but I can write similar conditions on arbitrary lattices. And it's actually very difficult. I actually do not know how to write actions which are not going to be exactly of this form. These actions are reminiscent of the actions that Djordje and collaborators in 2015. But as I said, these have Hamiltonian origins, so that's nice. But the question is really when will I get a single Chern-Simons section, and what is necessary to do that? And for now, the answer, as of today, the answer is I don't know. Maybe tomorrow the answer will change. But the idea that I do want to, the closest I can get to Simons is surprisingly by studying a confined phase of a lattice gauge theory, not a topological phase. Not so. If you took this theory and took the topological limit, G goes to 0, you would just get the standard toric code, the ZK version of the toric code, if you will, which will be described by the same old BS theory as just as a normal gauge theory, ZK gauge theory. It's only the confined limit, something interesting and different and new. So yeah, so with this, I will stop. I will open the floor. And I'll be here for 3 more weeks. So if people want to complain to me in person or have already resolved this problem while listening to me, then I am very happy to talk about this. So thank you.
You have questions? Yeah, no, wait. You are new. You are new to the business here. You have to speak inside here. Can I
Hi. About you mentioned the BF theory. So I remember that Kapustin has another paper about Z2 two-form gauge theory in 3+1 dimension. It's a sort of, I mean, he proposed a generalization of Jordan-Wigner transformation in 3 dimensions, space dimension. So I was wondering, I mean, in that case, there are Wilson surface instead of Wilson line. So I was wondering if somehow your, new variable can be, generalized in this higher dimensional case, higher form abelian theory.
Certainly, I mean, certainly there is a generalization of this curly X, if that's what you mean. In 3+1 dimensions, it'll just live on faces, of course, not on links.
Yeah.
I have no idea what the confinement of that thing will do. I have not thought about it.
Okay.
But it's interesting. One should think about it.
Okay, thank you.
More question or comments? Edoardo, you want to say something?
Okay, I can say something. Okay, thank you for a nice talk. I apologize for interrupting you too much before. About the second part of the talk, as you know, there is a history to this, and I was a co-author of a series of papers in the late 80s and later, which were corrected by Gordon Semenoff, who is on the audience, because there was a problem. I had a similar problem as yours, that the constraints didn't commute. And Gordon solved it for the original case of the square lattice, which we then extended to a large class, but not arbitrary lattices that this was done much more recently, actually. But the question, I mean, the fact that you're getting a double Chern-Simons theory is not surprising by this approach, because essentially time reversal is not broken in this theory. Essentially, by adding these 2 fluxes in the way you're doing it here, the breaking of time reversal by one is compensated by the other. And so whether you can write the theory in BF form or in double Chern-Simons, they are basically, well, they are not equivalent theories. They have many features in common. They have different tenion content, however. So this type of theories in particular in the continuum have been used by Adi Stern, who may be in the audience, I don't know, to describe fractional Chern insulators. And those are time reversal invariant states, topological phases of matter that are actually described by double Chern-Simons theory. So there is some history of that as well. Okay, that was going to be my comment. But the problem of how to write this explicitly with only a single one, in the action form, there are abstractions. You get analogs of doubling. Freilich had problems with that, of that sort. I don't think he ever acknowledged that, but there were problems with his formulation. There is a recent paper by Wen and I think Diego Dalmastro, who is maybe in the audience, that essentially insisted in having the fields to be periodic on every link, and which the theories that I wrote did not have. Mine were, quote, non-compact, at least at the formal level. So that's my only comment. But so the fact that you're getting a double theory is not surprising, since time reversal is not broken in your construction. Now, there is another symmetry that all of these constructions break, which is the point group symmetry of the lattice. So for instance, if you have only flux attachment in the way I did it by adding a plaquette in the northwest, that essentially is uniform in the lattice, but breaks the point group symmetries of the square lattice, for instance. And so does yours.
Sorry, I didn't get what it breaks.
The point group symmetry of the lattice.
Ah, the point group, okay.
The lattice has a point group symmetry, which is C4, okay, in the case of the square lattice. And this construction breaks the point group symmetry, as do all of the other ones, including the ones that I wrote. And so this is there's a question whether that point group symmetry is eventually recovered or not.
Okay, so yeah, so about the point group symmetry, I have no opinion. Like, I'm used to breaking symmetries on the lattice and having them re-emerge in some appropriate continuum. So I do not know what's the importance. For the time reversal breaking, I think I agree. So I think that there has to be a sense in which I sort of need to separate this theory in some way that will break parity, let's say. My ideas about what's going to happen is that essentially you need to somehow think of these kinds of operators as products of these individual operators like this that are sort of somehow gauged together, like through gauging their force, or through some D2 gauging or something, they're forced to sort of stay next to each other, and then to use this to use some version of Fermion staggering or something like that, to define just one chiral sector of this. But this is all very speculative. I agree. So trying to break the parity is the way to go to get a visual thing like this. I am not sure yet how exactly it's going to look in the end. And the third thing is you did mention a few references, which I unfortunately did not get. So I would be really, really thankful if you could either type them in the chat or send them to me, because that way I could actually have them for posterity. So yeah, I hope this is an acceptable answer given the technological issues. But yeah, thanks.
Okay, so thank you very much for the talk, and we stop here. Okay. Okay.